Hello everyone, welcome back to the next part of our tutorial number 2. You can find it under the Teaching tab on the group website, Teaching Lab 2, and this is the Environmental Monitoring and Modeling course 2017, currently being run at Charles Darwin University. My name is Shaun Levick, and this is a continuation of the lab which we started a few days ago, getting deeper into Earth Engine. So I'd like to acknowledge the Google Earth Engine team and their beginning curriculum documentation, which I've modified for this tutorial. So a couple of days ago we went through computing some terrain attributes using SRTM data, and we got to the point where we were ready to start playing with image bands. So what I'd like you to do now is head over to Earth Engine at code.earthengine.google.com. If you have a script already in place, please clear it. And we're going to search for the Mitchell Plateau, which is an area in northwestern Australia. Here it is, Mitchell Plateau. Let me just zoom out a bit. We are currently up in Darwin, and the Mitchell Plateau is a nice area of the Kimberley up on the north coast. It's challenging because there's often a lot of cloud in the area, so quite tricky to get cloud-free mosaics of satellite imagery in this region. Let's see what we can do in Earth Engine about that. For this exercise, we're going to be using Landsat 8 top of atmosphere the collection. So search for Landsat 8 TOA. Landsat 8 top of atmosphere reflectance. Let's import that and rename the collection to L8 for Landsat 8. Next, we're going to filter the collection with a few dates. So let's add a comment to ourselves. Filter collection to date range. Paste that in. So we're creating the variable filtered, Landsat 8, filter date, and 2013, April 15 to April 20. So quite a narrow date range. Let's run that and see what happens. Now we see these dark stripes appearing in our map. And if we zoom out a little bit, we can get a slightly better idea of what's happening. And these strips of data show us the orbital path of Landsat 8. Due to the orbit, we have to wait a few days, approximately 16 days, before the satellite revisits the same point in the Earth again. So just to quickly illustrate that, if we were to increase this date range a few extra months, heading up to July now, let's run that again. We'll find that there's a lot more data coming into our map view. For the purpose of this exercise though, let's go back to that narrow date range of just 5 days, and let's zoom in back to our area of interest. Hitting run. Now these look very dark. Why is that? With the default visualization parameters, the data looks dark and the colors look wrong. Pick better visualization parameters. So we just use the standard visualization, but if we add in some min and max criteria and specify which bands should be viewed, we'll get a much nicer looking set of results. So if we run that now, we get a true color composite because I've specified that we must use bands 4, 3, and 2, which correspond to the red, green, and blue channel, creating a very lifelike true color representation. Our next step would be to add a false color composite to this. So we're going to repeat the step that we've just done, except we're also going to specify a name for the layer. If I come back here and go to our layers tab, you'll see it just says layer 1, and that's because I didn't specify a layer name up in this section. In this next bit of code that I'm going to paste in, I'm now specifying that this combination of bands 4, 3, and 2 is the RGB composite, and this combination 5, 4, and 3, making use of near-infrared and red channels, is the false color. Let's run that. We get out the same true color strips coming back, and here comes the false color on top of it. Remember that the false color is very sensitive to chlorophyll and green vegetation. Now, these are visualization parameters that we'll often be using, so we can pull them out into a variable. For example, RGB vis equals min-max bands 4, 3, and 2. And if we do that, copy it, let's go back over here, and just to repeat that, we're creating a variable for the visualization RGB vis. That's why when we add the map layer later, we just need to call the filtered collection. We can specify the visualization parameters with one term and give that a name. When we run that, we'll see our strips again, and when you hover over layers, it'll be named RGB. Alright, now let's have a look at reducing image collections. So our first step is that we're going to expand out the date range. Let's copy this line, the middle line, paste it over here. Basically all we're doing is, instead of searching for images in a 5-day window, we're going to search for 1 year of data, basically the whole of 2014, and let's see what that looks like. So we see that the gaps between the overpasses have been filled in. We have continuous coverage, wall-to-wall coverage across the top end of Australia. Our layer is called RGB, that's what we specified, and that's really fantastic to be able to call up so much imagery so quickly, but we can see we have quite a bit of problem with cloud cover. What can we do about that? Well, let's first have a look at using the median reducer. So I want you to copy in this piece of code here, the very last bit of section 8. I'll talk you through it in a moment. Let's copy that. Actually, instead of pasting it over, all we need to do is copy the last line. And before hitting run, have a look at what we're doing. We're going to map add layer, the filtered collection, but whereas before we would load the whole collection, now we're going to just load the median value. And what that means is, for each pixel in this collection, we're going to drill through, order all the values, all the reflectance values in that stack, and then only map the median value to the whole image. So let's run that and see what it looks like. here comes our original image that we saw previously, with lots of clouds in the way. And it takes a little while to load, but we're now running the reducer using this median function. And because clouds have high reflectance, they have high values, and we sort through that 1 year of data, and it's basically a way of finding a good pixel within a year's worth of data. It's the median value, the general state of that pixel over the year. And as a result, we get a much cleaner looking mosaic. So we can switch off RGB underneath. Let's zoom in a little bit closer. Here's Broom, Derby, and we can see quite a bit of sediment washing out into the ocean, but a nice, very clear image. So that's great for looking at an average of a whole collection. But what if we want to pick out a particular image? Let's narrow the time range to a 7-day window. Paste over that now. So we're just doing, what are we doing here? 2015, September 1st. So let's run that. It's basically a 2-month window actually. And we can see we have quite a lot of data over our area of interest. We have cloud problems again. So let's add a region of interest using the point geometry tool in the import section, renaming the object to ROI. This will allow us to filter by bounds in a later step. So far we've used filter date, which allows us to vary our search according to a date range. Now we're going to use the teardrop geometry to add a point of interest, and we're going to rename that geometry ROI, which stands for region of interest. And when you look at this next code, which I'll paste in here, you'll see that we've added this line, number 4. So filter by date, we've done that previously. Now we add filter bounds ROI. That means we're asking Google to search all the available Landsat 8 images within this date range that intersect this region of interest point. Let's run that, and we'll see that only a couple of images pop up. So that's RGB, and we can see that's probably three different images that intersect that point. Now we're going to extract a sample image from the image collection and add it as a layer. So let's make a little note on what we're doing. We're going to extract a single image and have a look what's different about this piece of code. You'll see that we're filtering by bounds, but we're creating a variable image, which is the first image within the filtered collection. So let's run that, and I'd like to just rename that first so that we don't get confused. Run it again, and you'll see we have these two layers. This is the first, it's only just touching our little marker. But that's the first available image in the collection. So that's the way we can pick out a single image. We have covered cloud masking in other sections, and we'll get to that in more detail later. So we might want to filter the collection by the cloud cover metadata attribute. For now though, let's move on to computing NDVI, Normalized Difference Vegetation Index. We're going to do it the hard way first by using the mathematical operators. Let's copy this piece of code and write a note to ourselves. I'm going to compute NDVI, and let's see what this code is saying. Create the variable RGB viz, min max, use bands 4, 3, and 2. Create variable filtered, use the Landsat 8 image collection, filter by date to this period, filter bounds by our region of interest, and return the first image. That's what we've done already. That's what's given us this tile. So let's just delete those first few lines so we don't get confused. That's where we currently are. But this is the new section here. We're defining the variable red as being a band 4 selected from the image. Near infrared, image select band 5. The variable NDVI is going to be the near infrared, subtract red, divide by near infrared plus red. That's the NDVI equation. Near infrared minus red divided by near infrared plus red. We can then add the true color visualization to the map, and we can add the NDVI layer to the map. Remember that NDVI ranges from -1 to 1. So if we are searching in an area on ground looking for vegetation, we can set that to 0 and 1. Let's run that. This bit of code picks out our scene from the collection, and it's quite rocky country we're in up here, so there might not be a lot of green vegetation. Along the coast we are picking up these areas here. NDVI slightly higher. We can use the inspector to query these locations, and you'll see that this will return a value of NDVI, so 0.4, not very high, but higher than points on sort of bare rock. It would be 0.2. Okay. If we felt that this wasn't the best location for our just for our example, we could click on our region of interest, just drag it over to another point, say exit, and then all we have to do is rerun our code, and that will change our area of interest and bring up a new image for us. So extremely versatile, this tool. Really great capabilities. Now, we found a single image in a collection, and we've calculated NDVI for it. But if we want to build a time series of NDVI over time, we need to be able to map this function over the whole time series. So we're going to learn next how to write functions. So in order to continue, we're going to start by writing a function that adds an extra band to our images with NDVI data in it. The code for writing the function is as follows. Let's copy it and, as usual, paste it in and then have a look at it. I believe this is our first function for the course. Let's paste it in. So, variable RGB viz, min max, we've been through that before. The new bits, again, we can delete that. If we don't want to delete our previous lines of code, remember that we can also just use command / to comment out all of the previous code lines. So let's focus on writing the function. Variable RGB viz specifies the visualization using bands 4, 3, and 2. The function we're going to create is add NDVI to our image. And here we define NDVI as the normalized difference. This is earlier we calculated NDVI by dividing the near infrared and red bands, but it is a very common technique, so we can just use the normalized difference routine within Earth Engine. The format for that is just near infrared band and then the red band. And we're going to return an image called NDVI, which we will add as a band. We will then filter the Landsat 8 collection with a certain date range and ensure that it intersects our region of interest. We'll query that for the first image in the collection, and we will then say that variable NDVI equals add NDVI to the image. Let's give that a run. So, aside from looking quite dark, we have no errors. Let's see what's happened. Click on the Inspector tab, then on the image. Look in the Inspector tab results to see that the code has added a band called ND. Let's do that. If we click, we have RGB image, and we have an NDVI image with an extra band on the end. And this is the band containing our NDVI values. However, the default visualization hasn't picked up on that yet. Band 1 is being displayed by default instead of the ND band. We'll add a visualization parameter to correct this. You'll see how to do this now. We're going to specify that band ND must be used. So we'll copy that and we can just paste it over here and run that again. And now we have a much better looking NDVI image. Okay, now that we have the function, we're going to map it over a collection. That means we've developed a function for calculating NDVI for one image, but now we want to go back through time and compute NDVI for each image that's been collected over this point. Code to do that is here. We'll copy that. Paste it below. And can you see any differences between this part of the code that we've just copied in the previous part? The difference is that we've created a variable with NDVI, which is adding NDVI to our filtered map. So let's give that a run. Our true color composite and our NDVI bands. we removed the filter to return only the first image, and that's why we now have NDVI for more than one image. So we know that our mapping function is working. Our next step then is use the Inspector tab to click on the map and show that each image now has an ND band containing the NDVI. So we can click here and see that this tile now has an ND, and click here and see that this tile also has the NDVI value. That proves to us that our mapping is working, and now we are ready to almost ready to apply it to the whole image collection. But first we're going to get rid of some clouds. To do that, we're going to expand out the time range and switch to using the median reducer again, and that's to remove those cloud effects. So let's copy this script and we can paste that. Let's comment out our previous lines. Sometimes it's better to just comment them out than delete them, so that they're there if you need to come back to them. So for example, here I commented out too much and I'm mixing spaces and tabs, so that should work for us. Let me run that, and here we have a nice clean mosaic, cloud free for the whole map window. And we've successfully applied NDVI computation to all of these scenes. So this is a really great result. It's really quite amazing to be able to do this so quickly over such a large area. So what we've done here is mapped the NDVI function spatially across the different Landsat scenes. So we have a nice spatial composite. But the theme of this of the lab for today is actually time series. So what we're going to do next is work on an even better way to produce cloud-free mosaics, making use of the Earth Engine image collection quality mosaic, using this as a method for ordering image bands on a pixel by pixel basis. So let's give this piece a run. Copy that in. Let's comment out this piece for now and make a note that this is now called the Greenest Pixel Composite. Let's have a look at what this code is doing. Very similar to before, creating the function add NDVI and the variable NDVI, filtering by date, and adding our function to each of these images. We're gonna map out the median RGB, but we're also creating a variable called Greenest, and basically this is our best quality pixel, or the greenest pixel within the collection. So let's run that. We'll see that this is heavily optimized for work on land, for the terrestrial environment. So it's quite interesting over the ocean. It will often always pick us a pixel containing cloud cover, but on ground, if we zoom in, let's have a look along the highway here. The median value, the state of the land through most of the year. That's sort of the average condition of a spot on the Earth. The reflectance of that pixel over the year is the RGB median, and this is dry country, but this greenest pixel function is using the greenest possible pixel without clouds. So it's two very useful techniques for looking at and producing cloud-free mosaics. One is the average over the year, and the other is the greenest possible pixel. Very useful technique. Our last, or second last function for today is really getting to the crux of it now, is to be able to chart NDVI over time. So we're going to use just these extra, it's just one extra line here. Print chart image series with NDVI, select the ND band and intersect it at the ROI. So let's copy this, and we'll just make a little note here that this is the line for producing a TimeSeries chart. We've already done all the calculations needed. All that's left is to actually print the chart. So we're going to print that, and that's going to pop up in our console section. And here we have it, from February 2015 to October 2015. It's a little bit jagged. We're using a single point. In some of our further work, we'll use a polygon to average over a region, and that'll involve a few more steps. But this is a great way to quickly drill down through a time series and plot NDVI over time. What we can do quickly is just alter that date range a bit. Let's do it from beginning of 2014 up until present time. See what that looks like. And that's really the beauty of programming and using a platform like Google Earth Engine, is we're able to quickly adjust these date ranges and explore these patterns. As we extend this out over a longer time period, we can see what this starts to make more sense. We have these high values in the wet season. Remember, we're close to the tropics here, two very distinct seasons, wet and dry. As we start coming into the dry season, NDVI drops off. It's low through the dry, then starts picking up again when the rains come. Very useful for looking at these trends over time. Now, the last thing I want to show you today is how to export these images that we've created so that you can use them in another GIS program, or just download the high quality TIFF images. So the first thing to do is create a 8-bit RGB image object using the Earth Image Visualize command, and add it to the interactive map. And then we simply export that using the export image command, and by default that will go into our Google Drive account. So let's copy this piece. We'll call this create RGB object. Run that. And then we're going to export it to our Google Drive. Paste in this bit of code. So the important part here is the last line, export image RGB. I'm going to call the file Greenest Pixel. I'm going to run that. First you might think that nothing's happened, but have a look over here in the Tasks tab. We can see that this is another job I had running, but we can see tasks that are waiting for us, Greenest Pixel. That builds up. When we're finished with the project, we can decide which ones we really want to run. When we want to export this, we can then click on Run. We'll have a few options here. We can give the file a name. We can choose the resolution that we want to export it as. And we could either add this as an asset, pass it over to cloud storage, or simply save it to our drive. We run that. It'll take a little while to generate and save to the drive, but we'll then have that image available for use in other GIS programs. If you want to use it in another program, it's quite hard to imagine any functionality that's not possible within Google Earth Engine. Thanks very much, and see you in the next lab.